Okay, so I want to give a shout out to my colleagues, Dr. Joe Keebler and new doctor, he was a student at the time we did this work, Richard Simonson. We're all human factors psychologists in the Human Factors and Behavioral Neurobiology Department at Embry-Riddle, Daytona Beach. And of course, Ron and Nova Chemicals. And then the sponsor of this work was the Center for Operator Performance. Okay, so the presentation outline, study background, you already heard a little bit about that. And Ron will briefly go over that. The purpose of the study, then I'll talk about the method and in terms of the simulated scenarios, the measures, the procedure for the study, and then the results in a discussion. So this is a little, it is a study. Our objective was to determine the effectiveness of automation, in other words, the Safe Park app, and smart alarming in assisting process operators to detect problems and reduce flaring.
I don't think that mic's on. So it was in our ethylene 2 facility on the finishing side, and our goal was, our measure was flaring. So the simulator does measure flaring for us. So that's what the basis of the study was about. And our scenario was the propylene refrigeration compressor trip, which can take about 100 moves. And also we failed a control valve open a little bit. So that's what they had to detect after they responded to that. And there's lots of alarms that come in, of course. I'll cover that a bit more in the next slide. And I mentioned there's 100 steps, so we can go ahead one. I think you might have skipped one. Okay. So the alarming states we used, we picked on no rationalization. I just added 100 alarms after you got 3 or 4 pages. I could have added more, but I think we got the point. And the rationalization is the normal alarming that we use in the unit, and that's been set for a steady state operation, so we don't give the operator an alarm flood for certain situations. And on this propylene refrigeration trip, it brings in 150 alarms though when that machine goes down, because the whole process goes down. And then we developed a state on the simulator, smart alarming, so when we knew that this trip was happening, that it would only bring 5 alarms. And we could have reduced that. We just tried to come up with a kind of a constant number, so it was around 5. And the automation, the Safe Park application, does 100 moves, and it can reduce the time that it takes to isolate the process down from 20 plus minutes to 5 minutes. And yeah, and we use the, of course, high fidelity simulator for this as well.
Okay, so again, we were looking to quantify the effects of alarm design and Safe Park automation in terms of the human performance. And again, Nova provided the simulation. Embry-Riddle researchers, including myself, provided the experimental design and the statistical analysis. The hypotheses were very straightforward. We expected the panel operators to have lower perceived workload and perform better, i.e. have less flare when using the Safe Park app, so when using automation than without. And then also that the operators would have lower perceived workload and less flare when given rationalized and state-based alarming than without. Moving on to the method. So we had 2 independent variables. The alarm schema had 3 levels: no rationalization, rationalization, and then the state-based smart alarming. And then the second independent variable was automation, and it was if they had use of the Safe Park app or if they did not. So this created what we call a 3x2 design. It was a within groups design, yielding 6 different study conditions. How do you make the?
That line,
What?
this line in the middle.
Got it, okay. Where is it? What the heck? Oh, here we go. Okay, so for when using the safe park, one scenario and condition had the no rationalization, another rationalization, and the third, the state-based smart alarming, and then the same without that automation. All operators in this evaluation experienced all of those conditions. Okay, so the dependent variables, those are the metrics used to assess the effect of the independent variable on performance. And in this study, we had flaring volume, which was based on timing of the first alarm and anomaly detection that the some NOVA engineers calculated that for us. And then also the operator perceived workload using the NASA TLX. So the NASA TLX is a well-validated, commonly used way to measure workload. You actually can also get a little app that is the TLX if you're interested. I think if anyone is interested here, if you just type it into Google, then you'll find a little online version of it. But anyway, so it has the individuals rate 6 different aspects of workload: mental demand, physical demand, temporal demand, performance, effort, and frustration level. And so what they did was, in our case, we did paper. And so they would make a little hash mark of where between low and high on all these dimensions they were rating their workload. And so the lowest score, ultimately this is 20 points, we just didn't have it numbered. And so we then converted their hash mark to a number. Low is 1, high is 20 for each of those dimensions, and then we totaled them together. So if someone was reporting maximum workload on all those 6 dimensions, they would have a workload score of 120. All right, so the simulated scenarios, back to Ron here.
So I think I mentioned that propylene refrigeration compressor trip was the main event. The secondary event was valve malfunction, and the steps were the panel operator or the application would close the valves. The operator doesn't know which one has closed, that it is passing. It fails to close all the way. And it looks closed on the screen. We can go to the next slide here. Yeah. So this is an example of one of the malfunctions. We have an ethane storage drum, that flow controller 101 there. It would be shown closed on the graphic after the operator or the application closed it. And what the DCS shows is the output is 0, but actually the valve position was 24% in this case. And we don't have feedback from the valves necessarily, not on most of them anyway. So it would continue to flow into the exchanger, and eventually a high-level alarm would come in. Usually 2 alarms came in from different systems if it went on long enough. So that was the operator's key. They didn't know which system or graphic the problem might be on. So typically they were looking for alarms, and sometimes they were scanning graphics after they were completed.
Okay, so as I mentioned, the experimental design yielded 6 separate scenarios. And part of the art in scenario design is to have equivalent but different, right? So in aviation that I work with a lot, if you can think of, you want pilots to practice landing, but not always at the same airport, then it would be, okay, well then let's watch them, have them practice landing at Daytona Beach, and then have them practice landing at, I don't know, Ormond Beach somewhere, and so forth. So we had one scenario per experimental condition, but we had to have different scenarios for each of those conditions, right? But equivalent in difficulty. So we don't want to accidentally have we're talking flight, again, have one scenario, they land at Ormond Beach, and then another scenario, they land at Orlando International, right? Because the Orlando International is a lot more complex. Okay, so we're avoiding that. The panel operators, again, performed all of those scenarios, so all of the conditions, but in a different order to avoid learning effects and fatigue effects and so forth. So some people may have performed scenario one, A, B, C, D, E, F, I don't know how many that was, and another person maybe performed, you know, D, A, F, E, C, right? So different order. So the basic procedure was, this was part of their regular training. This was an evaluation and part of their regular training. So the panel operators scheduled for their simulation training day. We had already determined via random assignment what order of scenarios they would be performing. They arrive for training day, complete a demographic data form, and then Ron gave them their first scenario. After their first scenario, they completed the NASA TLX, had a short debrief with Ron, and then took a break. And then they would move on to their second scenario, rate their perceived workload with the TLX, have a debrief, go for a break, and so forth. So this ended up taking a full day, about 8 hours. There were 11 operators, finishing side operators in this. Their years of panel experience at the current plant was about 7.5, but it ranged from 2 to 18. Years of full all operator experience at the current plant was about 16.5, but ranged from 7 to 28 years. And total years as an operator, about 21, but again, it ranged from 12 to 31 years. They were in their late 40s, some mid-30s, some mid-50s, and then fatigue. We had them do a short, just fatigue rating when they began this in the morning, and it was about average. The scale was 1 to 5. So, the results. Okay, so for the statisticians in the room, we did do a multivariate analysis of variance with the 2 dependent variables, again, being perceived workload and the flaring. And then follow up univariate test and pairwise comparisons. Okay, so this next is going to show you the means. I know, you're in suspense. What is going on? Okay, so this is for perceived workload. And as you see, the pink circle line are with the Safe Park app, and the blue triangle line is without the app, and then these are for the 3 types of alarming schema. So here we have the no, the rationalized, and then the smart alarming. And we like the way this is looking here. This is for flare, right? So the first was perceived workload. This is flare. This time, the results are a little bit mixed. But again, we have the pink line for the Safe Park app, and then the blue for the no app. So the pink is below the blue on both of these, which is the direction that we were hypothesizing. Some funky's going on there. And we did end up with 2 significant main effects for automation and alarming, but not a significant interaction for the stats people in the room. So follow up, both the alarm independent variable had a significant effect on workload and flare, and the automation had a significant impact on workload on flare, but again, no interaction. And so this is what that looks like. So alarm schema aside, as you can see here, with the Safe Park app, the operators had a significantly lower perceived workload than without So the automation is doing its job in terms of lowering the operator workload. For Flare, again, with the Safe Park app, significantly lower flare released compared to without the app. Things got a little different when we were looking at the alarm schema. So here you see our smart alarm condition. They were the lowest perceived workload in comparison to the no rationalized and rationalized, separating out the Safe Park app, right? We hypothesized that the no rationalized would have been the highest here, right? So the fact that these were equal was odd, but certainly the smart alarming is down. And then flare was also a little odd. So in this case, there was a significant difference, but for some reason, this rationalized alarm had the highest flare. Okay, so what did we think of these results? So again, the purpose was to use a human-in-the-loop simulation study with upset scenarios and look at the effects on perceived workload and flare. There was a clear effect of the automation of that Safe Park app with lower perceived workload and less flare when operators had access to that app. The alarm design revealed mixed results. So there was lower perceived workload for smart alarms. But then the flare in both the smart alarm and the non-rationalized alarm were about equal. And so the question is, what happened in that one condition? And what we think is that one scenario in the condition where it was a rationalized alarm and no automation, that somehow it was inherently more difficult. Something was different about that one scenario, and Ron can also talk more about, about that. So limitations of the study, the scenarios we did not get to pre-test to see if they were equivalently difficult, right? And then also we had a very small sample size, which may have hidden some interaction effects. Overall, the prior research on alarm design does not typically, if ever, include human performance data, because to do this, we had to have a high fidelity simulator, and many companies do not have those, many organizations do not have those, so it was really awesome to be able to work with NOVA that has one and is using it actively and keeping it up to date and all of that. Again, clear evidence that the Safe Park app is reducing workload and flare. Future research is needed to refine scenarios for alarm schema tests, right? That's what we still believe our hypothesis is correct, but something happened in this study. And I just want to reiterate what Ron was saying about the benefits of human-in-the-loop simulation, that organizations can use them for all sorts of things, and ultimately using human-in-the-loop simulation-based testing can provide organizations both understanding of what's going on, and then in turn, how to make sure we're achieving maximal performance of our human-machine systems. And that's all. We actually do have a published paper discussing the study in detail if you're interested.